So if it is absolutely integrable by multiplying by this curve that decays this fast, then it must also be absolutely integrable if you multiply by something that decays even faster, right? So if you say this line is in the real region of convergence, then any value of s with real part greater than sigma 0 must also be in the region of convergence, okay? So this means that the region of convergence must be a right half plane, right? It must consist of all values to the right of some value, okay, of some line. Okay. Okay. So this is just a proof of what we just stated, but I think basically the concept is the same, right? So x of t is right-sided if for some t1, x of t is equal to 0 for t less than t1, okay? So by the premise of the property, if you say that this is in the region of convergence, then this means that x of t times e to the minus sigma 0t is absolutely integrable, okay? Which means that this integral, or this, is less than infinity. Now, suppose you pick a sigma 1 greater than sigma 0, then the integral, right, if you take the absolute integral of x of t times e to the minus sigma 1t dt, this you can write as the integral of t1 to infinity x of t times e to the minus sigma 0t times e to the minus sigma 1 minus sigma 0t dt. This is less or equal to e to the minus sigma 1 minus sigma 0 t1 dt. Okay. So this first equality, right, holds because, here I'm just adding a sigma 0 here and canceling it back, okay? And then because sigma 1 is greater than sigma 0, right, because sigma 1 is greater than sigma 0, therefore this value, this function here has the maximum value at t equal to t1. So I upper bound this by a constant e to the minus sigma 1 minus sigma 0 times t1, right? So this is the maximum value of this within this range, okay? So we have this maximum value times the integral of absolute x of t times e to the minus sigma 0t, which by the premise is finite, okay? So this thing is finite, right? So this is just working it out mathematically, but I think conceptually it's quite intuitive, right? If it's absolutely integrable for something that decays so fast, then it can, it must also be absolutely integrable if you multiply it with something that decays even faster, okay? Okay. So if you can say this for right-handed signals, then you can also say this for left-handed left-sided signals, okay? So again, if x of t is left-sided, right, meaning that it has non-zero values only to the left of some time instant, and you know that the line corresponding to the real part of s equal to sigma 0 is in the region of convergence, then all values of s for which the real part of s is less than sigma 0 should also be in the region of convergence. And this is for exactly the same reason as before. So if you have a signal that is left-sided, then its region of convergence must be the left half plane, okay? And if you have a signal that is right-sided, then the region of convergence is the right half plane. Okay. Now, what if your signal extends both to minus infinity and infinity, okay? So what if your signal x of t is two-sided? It's two-sided, okay? So a two-sided signal is something like this, right? X of t looking like this, that extends both to minus infinity to infinity. This is two-sided. But a two-sided signal is nothing more than just a left-sided signal plus a right-sided signal, right? So you can always view a two-sided signal as the summation of a left-sided signal XL and a right-sided signal XR. Okay? Okay? So if you view it from this perspective, then it becomes clear what the region of convergence would look like. Okay? Because we know that for a left-sided signal, the region of convergence must be a left half plane. And for the right-sided signal, the region of convergence is a right half plane. Okay? So for XL, its region of convergence may look something like this, right? It is to the left of some value sigma L. And for a right-sided signal, it is a right half plane, which means that it should look something like this, which is to the right of some sigma R. Okay? Now, if you want both of these to hold, then the region of convergence should be the intersection of these two. So assuming that sigma L is greater than sigma R, then the intersection will give you this strip here. Okay? Right. So if x of t is two-sided, and you know that the region of convergence includes this line corresponding to the real part of s equal to sigma 0, then the region of convergence will be this strip including this line, right? This will be the strip including this line, okay? Now, it is possible that XL is less than sigma L is less than sigma R. So what happens if sigma L is less than sigma R? Okay. So then the Laplace transform does not exist, okay, for that case, okay? So if sigma L is less than sigma R, then the Laplace transform does not exist. Okay? Now, let's look at one example for this. Okay. So suppose that we have a signal x of t that is equal to e to the minus b times the absolute value of t. Okay. So this is a two-sided signal. If b is greater than 0, then it decays on both sides. If b is less than 0, then it actually increases on both sides, right? So this is b greater than 0. This is b less than 0. Okay. Now, in any case, for this two-sided signal, we can split into two signals. One is we can split into a left-sided signal and a right-sided signal. Okay. So x of t, we can write as e to the minus bt u of t, which is the right-sided signal, plus e to the bt u of minus t, which is the left-sided signal. Okay. So these two terms corresponds to the form in examples 9.1 and 9.2. So we can directly obtain the Laplace transform, which is 1 over s plus b for the first term, and minus 1 over s minus b for the second term. Okay? The region of convergence for the first term is to have the real part of s greater than minus b, whereas the region of convergence for the second term is to have the real part of s less than b. Okay? So the region of convergence should be the intersection of both of these. Okay. So if you can combine these two terms to get minus 2b over s squared minus b squared with a region of convergence that goes from minus b to b. Okay? But notice that this holds only when b is greater than 0. Okay? So this region of convergence is non-zero only when b is greater than 0. Okay? Now, so suppose that b is greater than 0, then the region of convergence actually is the strip between minus b and b. Now, what happens if b is less than 0? When b is less than 0, then this tells us that the Laplace transform cannot exist. Now, why is it that it cannot exist? If you look at this figure here, right, this corresponds to b less than 0. Okay? So suppose you multiply this with a decaying exponential that decays to the right. So if you multiply it by exponential decaying to the right, you suppress this side, but still this side is going to infinity. So suppose you multiply it with exponential that decays to the left, you suppress this side, but this side still goes to infinity. So there's no way of choosing an exponential to suppress both sides simultaneously. Okay? Right. So the Laplace transform does not exist for b less than 0. Okay? All right. So let's stop here, and we'll continue next week.